Hello APC Mechanics students, in Unit 4, System of Particles and Linear Momentum, Class 3, 4.2 Impulse and Momentum, Part 1. Section 1, Linear Momentum. Given an object of mass m and moving with the velocity v, we define the linear momentum p to be the product between mass and velocity, where the SI unit of linear momentum is kilogram meter per second. Why so? The SI unit of mass is kilograms, and the SI unit of velocity is given by meter per second. Then the SI unit of the linear momentum would be given by the product of kg by meter per second. Now the linear momentum is a vector quantity, and it is known to be the quantity of motion. Why the linear momentum is a vector quantity? Because the velocity is a vector quantity and the mass is a scalar quantity. So scalar multiplied by a vector which give us a vector, which means that the linear momentum has a magnitude and a direction, It happens that for isolated systems the linear momentum is conserved. Then you can ask the following question: why to define a quantity given by the mass times the velocity, not for example the mass times the displacement? Because, as we shall see later, for isolated system the linear momentum is a conserved quantity, which makes it a unique quantity to be defined. Now moving on to section 2, Newton's second law, that we have already studied in unit 2, but now with a new fashion. Newton's second law can be introduced in terms of linear momentum, and it's given by F naught is to be dp by dt. Now here you can utilize this in two different ways: either the derivative of the momentum with respect to time, or the variation of momentum over the variation of time. But we know that P is mv, then we can replace P by mv. So here we have defined F naught to be dp by dt, and we're claiming that this is Newton's second law. Then what's the connection between this definition and the definition that we have done previously? Now if F naught is dp by dt and the linear momentum is given by mv, then we can replace P by mv, and in this case this is the derivative of m multiplied by v, so it would be the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first, given as follows. If the mass m is assumed to be constant, and this is the thing that we used to do in unit 2, we used to assume that the mass of the object is constant all the time, which means that this would end up being 0 because the mass is a constant, then the derivative of the mass with respect to time would be 0, and we're left with dv by dt multiplied by m. But we know from calculus that dv by dt is given by the acceleration. Then indeed again F naught, which is defined by dp by dt, is ma again, which is the same version that we have introduced previously. Therefore Newton's second law can be stated in two different ways: F naught is given by dp by dt, or even F naught is given by m multiplied by a. Both versions are exactly the same if the mass of the system during different processes is assumed to be constant. So if the mass is constant, both are exactly the same. We're free to use the first version or the second version. However, if the mass is variable, we should use the first version, because we're gonna have another term that take into account the variation of the mass with respect to time. Remark: if we're interested in determining the average applied force, this can be determined via large variations. So if we're talking about the average force applied, then dp by dt can be utilized as what? As delta p by delta t, because you know that dp is given by p final minus p initial, and delta p is given by p final minus p initial. What's the difference between both? This holds for small variation and this holds for large variation. Similarly for dt, which is t final minus t initial, and delta t, which is t final minus t initial. So if we're talking about the average force for a duration which is pretty large, then dp by dt can be utilized as delta p over delta t. Now let me state also some good example where the mass varies as the system evolves. So Consider a snowball which is rolling down a hill. As the snowball starts to roll, it will gain some mass, which means that the mass is varying, and in this case it's increasing. So we need to use, in this particular case, F naught is given by dp divided by dt. Another good example is a rocket launched upward ejecting fuel to provide thrust. Then the mass of the rocket is supposed to decrease, which means it's changing. Then here in this case we need to use F naught given by dp by dt, and we cannot use F naught given by ma. So here similarly we cannot use that F naught is given by ma. Now we're gonna state the impulse momentum theorem. Consider a force F applied on an object of mass m over a time interval delta t given by t2 minus t1. So we define the impulse j to be given by the amount of force applied over a time interval delta t or dt. So it's defined as an integral, which represents the amount of force Ft applied over a time interval delta t. The SI unit of impulse is Newton second. Why? Because the force is in newtons and the time is in seconds, so J would be Newton multiplied by second. The impulse is a vector quantity. Why? Because as we have claimed previously, if F is a vector and dt is a scalar, then scalar multiplied by a vector would give us a vector. Another expression can be derived for the impulse if we perform the integral and we apply Newton's second law. So basically this is the definition of the impulse. Now F can be replaced by Newton's second law, which is given by dp by dt. Now here in this case, this can be utilized as a fraction, so then dt with dt they cancel, and we're left with the integral of dp from t2 to t1, and that would be simply delta p, which is basically p2 computed at the instant t2 minus p1 computed at the instant t1. Now here, how do we understand the impulse? The impulse can be understood as a force applied over a time interval, and this might be confused with the work. The work, if you remember, it's the force applied over its displacement. However, the impulse is the force applied for a time interval. Now why the integral of dp would give us delta p? Because here the function is 1 and the integral of a constant would be a linear term, which is p. Now then the impulse is given by the change in momentum. J is delta p. So we have two different definitions for the impulse. Impulse given by the integral of f dt from t1 to t2, or which is given by the variation of momentum. And this is known as the impulse momentum theorem. Remark, both Newton second and kilogram meter per second are both units of impulse j and momentum p. Why? Because now we know that the unit of momentum is given by kilogram meter per second, and we know that the unit of the impulse is given by Newton second. So both of these two units are equivalent. Okay, so we can say that the unit of the impulse or the momentum are given by kilogram meter per second or in Newton second. If the applied force F is constant over the duration delta t, which is t2 minus t1, then the impulse is given by what? So if we're assuming that F is constant, then F can be dragged out. And here, what function do we have? We have the linear term, which is 1. Sorry, we have the constant, which is 1. And the integral of the constant would be linear, which is t, computed between t2 and t1. And that would be F multiplied by t2 minus t1, which is F delta t. Alright, so here what I'm trying to say, if the force F that we have applied is constant, then the impulse can be given by F multiplied by delta t. So let me do here a recap for you. Now the impulse is given by the general definition, which is the integral from t1 to t2 of F dt, which is also given by the change in momentum. So these two definitions can be applied anywhere, anytime. Now if the force is constant, then the impulse can be used as what? As F multiplied by delta t, simply because F can be dragged outside the integral. Now more of a graphical interpretation section 4. In this section, more interpretations will be added to graphic reading. Consider a curve that shows the variation of a force F applied on an object versus time t. So we have F versus T. Now we know that one graphical interpretation is the area under the curve. Such type of graphs has been interpreted previously to model interactions via Newton's third law. Moreover, this type of graph, which is F versus T, have been interpreted previously to dictate Newton's third law coupled with another graph. Now let's investigate the dimension of the area under the curve, which is given by F multiplied by T. Now F is given by Newton's, T multiplied by second, so Newton's second, which is equivalent to kilogram meter per second, which means that the area under an FT curve has a unit of Newton second, which represents the impulse delivered by the given force F, or even the change in momentum of the object. The impulse or the change in momentum may be positive or negative because we're talking about vector quantities. Area above the horizontal would represent positive impulse or a positive change in momentum. Area below the horizontal axis would represent a negative impulse or a negative change in momentum. Graphical features are not limited to area under the curve, but also x-intercept, y-intercept, slope, and the slope of the tangent as we have seen previously. And speaking of which, as stated by Newton's second law, that F is dp by dt, which means that F is the derivative of p with respect to time, which means that the slope of the tangent to a pt graph can be interpreted as the applied force, given a pt graph for a moving object. Now, suppose we are interested in finding the net force applied on the object at a specific instant t0, which is specified on the curve, referring to this definition because F is dp by dt, which means F is the derivative of p with respect to time, and this can be interpreted graphically by specifying a point, drawing the tangent, which is a straight line. Whenever we say a straight line, we determine the slope of the straight line. The slope of this straight line, which is the tangent to the curve, would represent the force itself. After that instant has been specified graphically, we plot the tangent to the curve and perform the slope calculation by choosing 2 points. This is the first point, and that's the second point. Then the net force applied to the object is equal to the slope, which is p2 minus p1 over t2 minus t1. Okay. Now recap. In the following table, I will try to list all the different graphical interpretations that we have visited through the course from the early beginning unit 1. If we have an xt graph, then the slope would represent the velocity, because we know that v is given by dx by dt. So the tangent to the curve, we can draw a tangent. The slope of the tangent would represent the velocity. If we're talking about a vt graph, we have two different interpretations, because A is dv by dt according to calculus. Then if we draw a tangent, the slope of the tangent would represent the acceleration, and the slope is the acceleration. However, if we do the area under the curve, the area would represent the displacement. Now for an AT graph, we didn't give any graphical interpretation. However, one thing which is important to mention, that the area under an AT graph would represent the change in velocity. Why so? Because if you multiply A times T, which is meter per second squared, times second, that would give you meter per second. So the area under an AT graph would represent the change in velocity, and by so we have visited all three types of graphs that we can encounter in kinematics, which is x versus t, v versus t, and a versus t. Now let's continue the plot. How about f versus x? This has been interpreted as an area for the work done. Now u versus x, if we do the tangent at specific instant, we do the slope, negative of the slope would give you the force, because for a conservative force we have fx is minus du by dx. So we do the slope or the tangent to a particular point, we can calculate the slope of this tangent, which is the line. The negative of the slope would represent the force. Now we know that for an ft curve, the area would represent the impulse or the change in momentum, and for a pt curve, if we draw the tangent to the curve, the slope of this tangent would represent the force itself. Now for the rest of the video, we're gonna solve some exercises, A ball of mass m falls vertically, hits the floor with a speed vi and rebounds with a speed vf. So let me do a sketch. This is the floor. So before impact, we have a ball that is traveling down with a speed vi. Now after that, the ball will travel upward with a speed vf. Now what is the magnitude of the impulse exerted on the ball by the floor? So we're interested in the magnitude. Now the impulse J has two definitions. Here we're gonna refer to the change in momentum, which is P2 or P final minus P initial. Now let's choose the direction which is up to be positive. Now P final is given by mv final minus the momentum, the initial momentum. Now this is the speed. So we need to include a minus sign to encounter or to take into account the negative direction, because this is downward, so that would be minus m minus vi. That would be mvf. Minus with minus would give you plus, so plus mvi, and if you factor out the mass, that would be v final plus v initial, which makes C to be the correct answer. Now exercise 2, a block of mass m is pulled by a rope along a horizontal surface with negligible friction for time t positive. The magnitude of the acceleration of the object as a function of time is given by the equation A as an exponential decay, where A and K are positive constants. Which of the following expression determines the impulse exerted on the block by the rope during the time interval from 0 to t1? So the impulse in this case can be utilized as integral from 0 to t1, as has been specified from this interval of f dt. We know that the force can be given as acceleration or mass multiplied by acceleration dt. The mass is constant, it will be dragged out. The acceleration is utilized as a e minus kt dt. Now here in this case, if you look at the choices carefully, no need first to determine the integral. Let's try to see if we have achieved one of the choices. So indeed, that makes E to be the correct one. Now a model rocket, we have the mass is launched from ground from 0 to 3 seconds. The rocket engines exerts an impulse of 45 Newton second vertically on the rocket. Assuming the mass of the rocket remains constant, we're interested in the average acceleration, so no need for an integral. We can set J is given by F multiplied by delta T, and we know that the force is given by M multiplied by A, so J is given by M multiplied by A multiplied by delta T. We're interested in A. Then A in this case is given by J divided by M multiplied by delta T. J, the impulse, is given by 45, the mass is given by 0.5. Delta T, which is the duration, is 3 minus 0, that would be 3 seconds, then multiplied by 3. Plugging this expression on the calculator, we're gonna find that the acceleration is given by 30 meters per second square, which makes T to be the correct answer. Now exercise 4, before we look at the question, notice it's a perfect graph, so we're either interested in determining the area or the slope. So here in this case, because they're asking us about the change in momentum, related to that would be the area from 0 to t. So the change in momentum delta p would be half base times height, that would be 0, that would be t, which is half the base is given by t, the height is given by f, so half ft, which makes C to be the correct answer. And exercise 5 as an exit ticket for today's video. The force F exerted on a ball during a collision with the wall is given by the function of time F, where alpha and beta. The ball first contacts the wall at t is equal to 0 and the collision lasts for 0.10 seconds. What is the magnitude of the change in momentum of the ball? Remember that they're asked about the magnitude. If the answer is negative, we need to change it to be positive. Since F is a function of time and we're not asked about the average, then we need to utilize the change in momentum as an integral. We know that J is given by delta P, and also J is given by the integral of F dt from t1 to t2, which means the change in momentum is given by the integral from t1 to t2 of f dt. Now the initial instant is given by 0, the final instant is given by 0.1, the function is given by alpha t minus beta t square dt. Now alpha and beta are constant. This is linear, would be quadratic, quadratic would be cubic, which means that would be alpha t square over 2 minus beta t cube over 3 computed between 0 and 0.1. Now that would be alpha 0.1 square over 2 minus beta 0.1 cube over 3 minus the same expression computed at 0. Now basically you can ignore all of that because it's 0. Alpha is given by 400 multiplied by 0.1 to the power 2 divided by 2 minus beta, which is 4000 multiplied by 0.1 to the power 3 divided by 3. Now plugging this expression on the calculator, we're gonna have the following, which is 2 over 3, and the unit of change of momentum is given by kilogram meter per second, which makes, so 2 over 3 is given by 0.67, which makes B to be the correct answer. Then thank you for watching and see you soon in a new one.